Welcome back, viewers, to the remaining part of the first lecture. I have already introduced the concept of functor here, where the functor can be thought of as a mapping from the category C to the category D. So the objects of C get mapped to the objects of D. So are the morphisms from the category C to the category D. So that certain compatibility is meant to be satisfied. Compatibility is given by the fact that f, the functor of these, the functor f acting on this morphism is a morphism in the category D, which has to be the same as the functor acting on the morphism G composed with the functor acting on the morphism F. And the functor acting on the identity morphism on X has to be the identity morphism on the object Fx of the category D. If these properties are satisfied, we call the map between the two categories F functor. All right? Okay. So there is one other thing related to the delooping of the group that I wanted to mention. I think I forgot to tell you about that. So the delooping, when you have a group, so I'm going back to the delooping of the group. I forgot to mention it, but it's an important thing to discuss, so that's why I'm going back there. So when we start with a group, we can form a category of the delooping of the group, which is actually a groupoid, like I discussed in the previous segment. The delooping of the group, which is a category, in fact, it's a groupoid, and that can be expressed diagrammatically by a single object dot, and the morphisms are precisely the corresponding group elements, which are drawn like loops here, okay, where there is a distinguished loop called the unit of the group. So this is how this groupoid is presented, which is a category. All right. So now we have all the elements that we needed to make the theory, to convert to be more precise, to tell you how the group representations can be translated in the language of category theory. We know what it means by a group. We know what it means by a category. We know what it means by a functor, being a map between two categories. We know what it means by a monoid. We know what it means by the looping of a group. Okay, so here is the category theoretic definition of a group representation. Let G be a group. A linear representation of G is the functor R from the delooping of the group to the category vect C. Okay? We explain what it means by this category vect C. We explain how to obtain this delooping of the group category, and we explain what it means by a functor. So the representation, as we discussed, as a homomorphism from the group itself to the invertible linear map on a given vector space, can be translated into this language of category theory. Now, let me explain. So first recall what information a functor provides. Object and morphisms of BG. There is a single object in BG, and there are morphisms there corresponding to the group elements of the group. So the object, the single object, and morphisms of BG should be mapped to objects and morphisms of vectors C in a compatible way. Okay? We explained what it means by compatible way earlier. So let me first of all denote a single object dot of BG is mapped to an object of vect C. That is a vector space. That is a vector space. Let us denote this vector space with V. So if we denote this functor as R, then R of the single object is precisely V. All right. Now, what about the story of a morphism? For each morphism of BG, that is for each element G of the group, we need a linear map. We need a linear map RG from V to itself. Okay? In other words, this linear map is precisely a morphism in vector C. Using pretty standard argument, one can show that this map is invertible. One can prove that this map is invertible. Therefore, we conclude that this functor R from this groupoid to vec C induces a group homomorphism. I told you what it means by homomorphism earlier. G to GL V. This is the usual definition of representation. Okay? So, it means that under the functor R, the morphisms here are mapped to invertible C-linear maps in this category. But in this category, there are morphisms which are not invertible. They don't have pre-images under this functor in BG. Okay? So only those morphisms have a pre-image under this functor which are invertible. This is given by this statement that Rg from the vector space to itself is invertible. Okay, so to extend this idea to the next level, we see that if we can choose a different vector space from this category and construct a different representation R1 from the category BG to vect C again. So we can keep producing representations of G in this way. The collection of all such functors R, R1, R2, R3, and so forth form a new category called the category of representations. It is an example of a more general concept of functor category that we'll discuss in detail in due course. This finishes the first lecture formally. So let me summarize what we did in this first lecture. I want to make a summary of what we studied in the first lecture. The first lecture is about how we translate our known ideas of mathematical stuffs into a new language, a universal language, so to say, of category theory. For these, we define an abstract group first, then we gave the definition of a category, following which we showed how to construct the delooping of a group, which is of course a category, and then we have seen that if we relax the inverse law or the inverse properties of group, we still have the delooping construction resulting in a category. This way we motivated the definition of monoid, and the looping of a monoid gives us also a category. Then we studied the basics of representation, the group representation. We defined the group representation for an abstract group, following which we gave the example of a very important category vect C, and then we introduced the notion of a functor, which can be thought of as a map between two categories under some compatibility conditions. We also studied those compatibility conditions. And after that, we finally showed how group representation can be thought of as a functor from the delooping of the group category to the vect C category. Yes, so this was the content of the first lecture. So I don't want, as I stressed in the beginning, I don't want you to understand the fine details of the first lecture. You're not expected to do so, since you don't have enough background to understand every fine details of the first lecture. But you need to have the big picture, the motivation of studying category theory. So in the following lectures, we will follow the textbook by Spivak, starting from the sets and functions. We'll start with the study of this category SED. It is a category where the objects are sets and the morphisms are functions between the sets. So we will explicitly study this category and study different abstract notions of category in terms of these category of sets. Various abstract notions. That will be our goal for the first phase of the course. In the second phase of the course, we will move into the more abstract idea of category and functors. Okay? So in the next lecture, I will give you a brief outline of the course, meaning that the stuff that we are going to cover for the rest of the lectures of the course. I will give you a tentative outline. And what else? Whatever we studied in the first lecture, I will later it up and make a PDF of it and share it with you in the Google Drive. Thank you all for attending the lecture. We will meet again next week. Thank you very much.